This is a lesson on vector products as a primer video in the basics of calculus for physics. So we're going to look at how vector products are done. I don't have any examples for physics. That will be in a lesson associated more with physics concepts, more specifically work and energy and torque for intro level physics. So a few things I wanted to dredge up for us just to keep in mind as we move forward. I might not use them during this lesson, but I wanted to remind us all about right triangle trig. We can use trigonometry in order to relate the legs of a triangle. We have the Pythagorean theorem. I wanted to remind about scalars and vectors. If you're in physics or in math, you may be aware of the difference between scalars and vectors. Again, a scalar is any quantity that has magnitude in no direction, and a vector includes the direction information as well as the magnitude. And important here, because we're looking at directions, you need to explicitly sign a coordinate system. We could be in one dimension, which is just a number line, or 2-dimension Cartesian coordinates, 3 dimensions, 4D, up to ND. I work in physics, so we could have, 9D. Always assign your coordinate system. Need to know which direction is positive. Direction is specified by a plus or minus sign. Okay, and we're going to note some choices are more useful than others. If you have an opportunity to mindfully assign a coordinate system, make sure that you choose one mindfully that is going to be wise for your situation. A few other things here I wanted to talk about vector decomposition. We are looking at x and y components, x and y and z components, or any in the other dimensions. So knowing how to decompose them and also keep the right sign. So if you're decomposing, for instance, a vector in the second quadrant, you would have a negative x component and a positive y component. So make sure you keep track of your signs so that your math works out correctly. Also, if you work in polar coordinates, this may not be a lot of people, but if you work in polar coordinates where you're given a radius and an angle, you can always convert those to Cartesian coordinates with an r cos of the angle and an r sine of the angle. Okay, so you can do dot and cross products with the r vector. That's something you can do. There's a tangential vector that's perpendicular to it, but I'll leave that for another lesson. Vector notation, just so that we're clear, or if it's still weird for you to reiterate it. When we talk about vector notation and we're looking at the components of a vector, we can say that vector A has a component in the x direction, and we note that it's in the x direction by using the I hat vector. I know it's weird, maybe we should use an x hat vector, but that's what I means, is in the x direction, j hat is in the y direction, and k hat is in the z direction. And you can see that over on the picture here. Here's the y component in the j hat direction. It lies along the y axis. I, j, and k are actually what were called the unit vectors. Just like there's a unit circle of radius 1, unit vectors have length 1. So k is 1 in the x direction. In the z direction. Okay, so that's what k hat means. It's 1, the length of 1 in the z direction. We can write vectors as components like we would. It looks like a point, and I just wanted to reiterate, but there's brackets on the end. We call this a bra and this a ket. So there's brackets on the end, and this means that it's a vector. That quantity is not a point, it's a vector. Okay. So as we're moving forward, and the reason I'm doing this video is it's called vector products, and I wanted to clarify vector products from vector algebra. So vector algebra starts with simple things like adding and subtracting vectors. So if I have vector A and add it to vector B, this can be, the order doesn't matter, it can be switched around, and I just add up all the x components in A and B and all the y components in A and B and keep those in the x direction or the y direction, and I can add or subtract vectors. Subtracting vectors is just adding a negative vector. Multiplying a vector by a scalar. So if I take vector A and I put some sort of just constant in front of it, maybe alpha equals 2. I'm doubling it. I'm scaling it. All right, I'm just making A twice as long. Well, what happens is that can get distributed throughout the whole, so that, I have the new vector will be twice the original vector in the x direction and in the y direction and in the z direction. I can also scale an addition of vectors. I just distribute, if this was a 2, I'd distribute it to both of those quantities, and I'd have twice a and twice b, and that would equal twice a plus b. Notice that multiplying by a scalar is going to be different than what we're doing when we actually multiply two vectors. Instead of having a plus b or something times a, which, technically this is multiplying, we're actually going to take two vectors and multiply them together. And we have two results. There's two results we can do this, and why I mentioned scalars and vectors earlier. The first result we have is what we call a dot product. That's the first result. Scalar product, we could call it. Because it results in a scalar quantity. So if I take vector A and I dot it, notice that the sign we use here is a dot. It's a dot product. Dotting A into B is the same as dotting B into A. We can change the order here. And what we do is we take the magnitude of A, the magnitude of B, and cosine of the angle between them. So that's why I included the picture over to the side on the right here. Is there's vector A, there's vector B pointing off into space, and there's some angle between them. If you would be proper in math, you might say the magnitude of A is enclosed by two absolute value straight lines, and then the magnitude of B and the cosine of the angle between them. I leave the signs off for the magnitudes and just write the letter without a vector sign over it. Okay, so that's what these mean, is the magnitude of those two vectors, however long they are. So the length of A, the length of B, and cosine of the angle between them. I'm going to remind you that if you have components of vectors, we can find the length of them with Pythagorean theorem, and we will do that later in this lesson. What does a dot product tell us? A dot product tells us how parallel two vectors are, okay? Because I have this cosine dependence in here, all right? When you look at a technical definition of what a dot product is, it's the orthogonal projection of one vector onto another, and that's what these pictures down at the bottom are. If I look at the first one on the left, it's projecting A down onto B at a right angle between them, and this is the length of that vector. And then I multiply by B, and then I get A dotted into B. As conversely, if I take B and I project it orthogonally onto A, there's a right angle right there. Orthogonal means perpendicular. So this is B cosine phi, this component right here. And then if I want to find the dot product, I multiply by A. And you can see that this term here is the same as this term here, whether I project one vector onto the other or the second onto the first. All right. So when I look at how parallel they are, right, that's what I mentioned, is why do we use dot product? Well, it is a measure of how parallel two vectors are. If there is an angle of 0 degrees between them, I get cosine 0, right? Cosine 0, if they're parallel, I get cosine 0 degrees, and cosine 0 degrees is 1. That's the maximum value it could be, the dot product could be, is when there's no angle between them. If they're anti-parallel, then the angle is 180 degrees, and cosine of 180 degrees is -1. So if I get a negative sign out of the dot product, and this is very important if you're doing physical applications, but also just noting in general in your math, is if the vectors are pointing anti-parallel in any way, you will get a negative dot product. If the two vectors are completely perpendicular to one another, the angle is 90 degrees and we get cosine 0. So that's why a dot product is an easy test of whether two vectors are perpendicular to one another, or if they're parallel, because if it is 0, they are definitely perpendicular to one another. If it's any other value, they're either somewhat parallel or somewhat anti-parallel. So this is the general form if you know how long A is, how long B is, and the angle between them. We may be just working with components. So the dot product with components yet still results in a scalar quantity. And what we're going to do is we're going to dot these two vectors together. And notice that I have the two vectors written out here in their components. I have ax I hat plus ay j hat plus az k hat dotted into bx I hat plus by j hat plus bz k hat. Now, we are going to multiply these two vectors together as if we were doing just regular trinomial multiplication. So I would take ax I hat and dot it into bx I hat and by j hat and bz k hat. And I do the same with ay j hat, do the 3. So I get 9 terms overall if you're seeing how this goes. But what I'm going to note down here, the note down here, is that if the two components are in the same direction, and this is the thing about if they're parallel, if the two components are parallel, I'm going to get the dot product equal 1. If I take two components and they're not, like here I hat dotted into j hat, so if there's an x component and a y component and I dot them together, those are perpendicular to one another, and I'm going to get a result of 0. So the 9 terms that multiply out from here actually become just 3. There's only 3 of them that are non-zero. The I hat dotted into I hat, the j hat dotted into j hat, and the k hat dotted into k hat. And so ax times bx times I hat dotted into I hat, which I know is 1. This is 1. So that's why this turns into a scalar. So it's times 1 here, times 1 here, times 1 here. All of the vector quantities get dot producted out, and I'm just left with a scalar. I will end up with a number on the end of this. Okay, so I'm going to take ax times bx, add on ay times by, and if I have more dimensions, I keep doing that along all the dimensions. So that's how you do a dot product if you're given components. We can relate the two. If I know the dot product of given components, I could relate it to the dot product given the magnitude of the two vectors and the angle between them. So I picked some problems for us to practice on. This is practicing dot products. We're just going to use the equation and get used to doing a dot product. Okay, so I have vector u, -6, -4. I don't know where it starts and ends in space, but I know its components are -6 in the x direction and -4 in the y direction. V has -6 in the x direction, +4 in the y direction. So I'm going to use, because I was given the components, I'm going to use the second version of this equation for finding the dot product. I'm going to take ax times bx, and I'm going to add on ay times by. So ax times bx is -6 times -6. I'm going to add on ay times by, which is -4 times -4. Sorry, times 4. And so that's 36 minus 16, which is 20. That's it. That's the dot product between those two vectors. Let's do it again in 3 space. I'm going to do x components multiplied together plus y components multiplied together plus z components multiplied together. So -5 times 4 plus 4 times 10 plus -4 times 16. -20 plus 40 plus -24. And you will note that this is 20 minus 24. This turns into -4. And that's it. For as complicated as this equation formula can look like, once you learn how to put the mechanics together, it should be pretty easy. You're multiplying and adding. You're not doing anything fancier other than that if you have the components. Notice part C here is a vector in 4 space. So we're just going to do the same thing that we were doing on the first 2 parts. I'm going to take the x components and multiply them together. I'm going to add the y components together. I get 4 times 0. I'm just going to put 0 here. The z components, I get 0 and 0. And then in the extra dimension here, you could call it the, I don't know, W dimension, whatever you want to call it in there, -3 times 5. So I get -10 plus -15, and you can see that this is a -25. Okay, so even when the dimensions get larger, the dot product is still pretty easy to calculate. I made the example easier by putting some zeros in here. You may have some non-zero values, but that's how you do the dot product using the components. The next problem here, unknown vector magnitude. Let's read this problem and see what they're asking, what they give us and what they're asking us to find. For the vectors u and v, suppose the magnitude of u is 3. So if I write this out, this is how I would write it. U equals 3. I don't write the bars and the vector over it. I just simplified it and write u equals 3. The angle between the vectors is 25 degrees, so I can write that out, 25 degrees. And the dot product, so they give me the value of the dot product equals 10. And it says find the magnitude of vector v. So they want to know what v is. So because I'm giving an angle, I'm going to look at the first version I introduced to you, the AB cosine phi. And they actually gave me the dot product. So I'm going to write this out. U dotted into v equals the magnitude of u, the magnitude of v times cosine of the angle between them. I know this quantity is 10. They tell me u is 3. They tell me I need to find v, and I have a cosine 25. So doing a little bit of algebra in here, not a big deal, just one step, 3 cosine 25. And that's how I would find v. And when you run this through your calculator, you should get 3.678. No units, we weren't given any units. So that's the magnitude of v. So I can use the relationship, if I know the dot product, I can use the relationship to work backwards, which shouldn't be a surprise. We like to do that in math. Can you use an equation or formula backwards and forwards? Let's look at this next problem. I chose to emphasize the idea that the dot product gives an idea if measure of how orthogonal two vectors are. It says there's two examples here. One's in 2 space, the other's in 3 space. Are the vectors orthogonal? If not, determine the angle between them. Okay, so I put the coordinate system over here for the first example, and I can write this out. I can look at the picture here. If I draw these two vectors, if I have 2, 7, and I'm just going to start them at the origin. They could be out in space somewhere, but I'm just going to start them at the origin so that we can see the angle between them. So there's 2, 7, and then I have -3, 4. So there's -3, 4, and I see that the angle between them is not 90 degrees. So when I do this dot product here, I will not get 90 degrees. I will get some other value, or I won't get 0, right? If they're orthogonal, then I have 90 degrees between them. Cosine 90 equals 0. So I will get a non-zero value here. I wonder what I will get. So let's do the two dotted into each other. So then I get 2 times -3 plus 7 times 4, which is -6. Plus 28, which is 22, a positive 22. So that's the dot product between these two. It doesn't tell me anything about the angle yet. It just tells me what the dot product is. Well, I'm going to play the game that I did on the previous problem where now I know the dot product and I can solve for another variable in the equation. If you look at this, I can find the magnitude of that first vector. The magnitude of that first vector is going to be 2 squared plus 7 squared, and then square root that. All right, so I get 4 plus 7. I get 4 plus 49, which is the square root of 53. So that's the magnitude of that vector. I can also do the magnitude of this vector, but I'm going to kind of cheat on this. I already noticed it's 3, 4. We know about 3, 4, 5 triangles. So I get, 9 plus 16 square root, which is the square root of 25, which is 5. So I know the magnitude. So if you're looking at this equation up here, I can do A dotted into B equals the magnitude of A, the magnitude of B, cosine of the angle between them. So just to be explicit, I know A dotted into B is 22. I know A is the square root of 53. I know B is 5. And now I can solve for the angle between them. So the angle between them is going to be the inverse cosine of 22 divided by 5, the square root of 53. And when you run this through your calculator, you will get 52.82. basically is what you get. And when I look at that on the diagram, right, that's why I drew these vectors, is that's this angle right here. That's what phi is in there. That's that angle. Okay. So using the dot product, and like I mentioned before, because we know Pythagorean theorem, we can find the magnitude of those two vectors. If we know the x component and the y component, we just use Pythagorean theorem and then use the formula like just solving for an unknown angle. Okay. If I look at the next example, let's see if these two vectors are orthogonal. So when I multiply this out, I get 1 times 4 plus 0 plus 2 times negative 2. So we get 4 minus 4, which equals 0. So I'm going to say, yes, these are orthogonal. They're perpendicular to one another. I could try to draw this in 3 space here. Okay. The first vector, let me make blue. 1, 1, 2. Okay, so if I go 1 in that direction, so here's x, here's y, here's z. 1, 1, so there's the 1, 1. And then if I come out this direction, I'm going to have the vector pointing like in this direction. Okay, so hopefully you can see that in 3 space there. Let me draw the other vector. The other vector I'll use red. We have a positive 4, so 1, 2, 3, 4. 0 in the y, and then negative 2 in the z. So this vector is going to lie on the xz plane, and it's going to point off in this direction. So what I'm saying is this angle right here, which is in 3 space, remember some of it's coming out of the page at us, that's a 90-degree angle between those two vectors in 3 space. So that's what the dot product tells us, that they're perpendicular. So several different examples of how to use the dot product. You will be in physics, you would use it with work. We dot a force into a displacement vector and see if those two are parallel. And work will come out as a scalar quantity. Work is an energy, which is a scalar quantity. So that's how you would use it in physics, and you can look for a future video on that topic. I want to move forward to cross products here. Cross products are the second type of multiplying vectors together. Notice that I'm using a cross in here, a multiply sign. This is what we indicate with a cross product. And this results in a vector quantity. A dot product results in a scalar quantity, and a cross product is also called a vector product because it results in a vector quantity. Okay, so we have our vectors A and B and some angle between them as we had for dot products, but we're going to, instead of have the cosine in there, we have the sine. And what this does, notice like what does a cross product do is it gives a measure of how perpendicular two vectors are. If they're parallel to one another, then that angle between them is 0, sine 0 is 0, and that's how we would know they were parallel by the cross product. If they're perpendicular to one another, sine 90 is 1, and you would get just the magnitude of the two vectors multiplied together. Notice that up top here, I have the absolute value sign, or the magnitude of the vector around this, because this is the magnitude. This is how you would find the magnitude. This gives only a scalar quantity. In order to find the direction, I have to use right-hand rule. So this is where we start getting into the vector nature of the cross product, is using the cross product as a right-hand rule to cross vectors into each other. So I typed out the instructions here. I'm going to read them, but then I'm also going to walk you through it with the picture. So I said, put fingers in the direction of the first vector. And what I'm going to notice, I did not say A crossed into B equals B crossed into A. That is not true. When I am crossing products, order matters. And I'll write that up here. Order matters with an exclamation sign, okay? Because it results in our direction. Put fingers in the direction of the first vector in the cross product. Swing your fingers or your palm into the direction of the second vector, and whichever direction your thumb is, that indicates the direction of the cross product. So in the first picture, on the to the right here, so I'm looking at A cross into B. They've let A be directed towards the left and B be directed towards the right some. If I put my fingers in the direction, I'm just holding my palm like I'm waving hi at someone, okay? And so I'm going to put all of my fingers in the direction of A, and my thumb happens to be pointing up. It could be pointing down. My fingers are in the direction of A if I point my thumb down, but it's pointing up. And then if I cross into B, right? And it has to be less than 90 degrees or less than 180 degrees. If I cross the other direction, I'm going 270 degrees, and that's not how I want to go. Cross A into B, and I'm going to note that my thumb points upward, and that's the direction of the cross product. Notice in the second diagram on the right in this picture, I cross B into A, so my first vector is now B. If I put my fingers in the direction of B, it points along B, and my thumb's actually pointing down as I cross my fingers into A through that 90 degrees between them, so that the cross product results in a downward, which they're indicating is negative in this picture. Okay, so I will work more with the direction of the cross product in class, especially as we're working with the concept of like torque and which direction a torque will be. So let's take a look at how we do a cross product with components. I did this with the dot product. So a cross product results in a vector quantity. When I multiply these two vectors together, I'm doing it with a cross product sign, and I'm going to do the same thing I did before, is FOIL this, right? I'm going to multiply all terms by each other, and I should get 9 of them out. So let me do the first couple. AX I hat crossed into BX I hat. That's the first term. And then I would add on AX I hat crossed into BYJ hat, and then so forth. Okay, and I get 9 terms altogether. And what we're going to do is simplify them like we did before. So when I look at this note, and I did this with the dot product as well, when I look at this note, some of these terms are going to be 0. The terms that are going to be 0 are the ones where the two components are completely parallel to one another. I hat crossed in the I hat, J hat crossed in the J hat, and K hat crossed in the K hat. So this first term here, that turns into 0. And what I'm left over with when I do that simplification are all the cross terms, right? So this is sort of where the name cross product comes from. All the cross terms are left over. This will be AX times BY multiplied by I hat crossed in the j hat. And when I look at what I hat crossed in the j hat is, I have that down here in this line here, and it may be something you want to maybe put on an index card or figure out how to remember. I hat crossed into j hat is a positive k hat. So instead of writing I hat crossed into j hat here, I'm just going to get rid of all that and write k hat. And when I go through and I look at the 6 other terms that come out of multiplying these two vectors together, I'm going to get 2 k hats, I'm going to get 2 I hats, and I'm going to get 2 j hats. And some of them are going to be, half of them are going to be positive and half of them are going to be negative, because notice if I multiply them in the opposite direction, if I do the cross product, and we saw this on the previous slide, if I cross two vectors in the opposite direction, it gets the negative value of it. Okay, so when I gather all those terms up, I get a much longer and somewhat more intimidating formula here for a cross product if I know the components of the vectors. And to be honest, this is where I'm going to note that having linear algebra class, or at least knowing how to find the cross product using a matrix, is helpful. So when I look at a matrix, what I'm doing is I would be finding the determinant of this matrix. I, j, k is the first vector. Ax, ay, and az is the second vector. And then bx, by, and bz is the third vector. And I would be finding the determinant of that. So if you know anything about determinants of matrices, instead of remembering this long formula down there, you can use the determinant of this 3x3 matrix. Either way is fine. I may use either as we go through these problems. I find that when I do this, I anchor myself more in the matrix method because it helps me remember what to multiply together and where negative signs go. But either method, again, is fine. So let's practice some cross products. Let's just do some. Now that I've told you how to do it and what it represents, let's practice some. Find u crossed into v if u equals -2, 0, 2, and v equals 1, 0, 5. So I think that I don't need this picture over here. We're definitely not in 2 space anymore. I mean, I could do 3 space on this. I could. -2 in the x direction, 0 in the y, and +2. Let's just draw a z in here. +2 in the z. So that would be a vector that looks like this in space. That would be the first vector, -2, 0, 2. And it's in the xz plane. The other vector is also in the xz plane. So I have 1, 5. So 1, there's 1. And then I'll come out with, that's 2, 3, 4, 5. So then there's 1, 5. So I'm going to note that the angle between these two vectors is not 90 degrees and it's not 0 degrees. So I'm going to get some vector in space. When I cross them, I'm going to note, can we note here that the angle between them is here, and both of these vectors lie in the xz plane. This is an xz vector and this is an xz vector. When I cross them, what happens is the cross product is going to be perpendicular to both of these vectors. So I know the cross product's either going to point straight upward or straight downward in the y hat direction, in the j hat direction, right? I crossed into k equals, what is that, -j hat, or k crossed into I is a +j hat. So the cross product is one of these red vectors. Okay, so let's do this mathematically. I'm going to use the second equation here. I don't know the angle between them, so the first version of the formula won't work. The second one is when I have all the components and I'm going to multiply them together. Again, like I mentioned, I'm going to take the determinant, and this is, I wrote it out this way and I think it's useful, is to say if I want to find the I hat component of U crossed into V, I'm going to do the determinant of the 2 by 2 matrix of the XZs, of the YZs, of the YZs. So U has YZ component of 0, 2. The V has YZ components of 0, 5. I'm going to subtract. Notice there's a subtract sign here. The J hat is going to be the determinant of the 2 by 2 vector of the XZs. I'm going to leave Y out here. So I'm going to have negative 2, 2 and 1, 5. And then the K hat, I'm going to add on the K hat component, and it's going to be the 2 by 2 determinant, the determinant of the 2 by 2 of the XYs. So negative 2, 0 and 1, 0. So when I multiply these together, and that's why I like putting it this way, because then I can kind of see what I'm multiplying together a little bit better. So I'm going to multiply AX times BZ. Did you see how I did that? This is AX times BZ, so 0 times 5. And then I'm going to subtract AZ times BX, which is 0 times 2. 0 times 2. Overall, and this is all in the I hat direction, overall I'm getting a 0 in the I hat direction, which is what I expected, right? I said that when I get done with this, I expect only a Y component. So let's do the next one here. I get minus AX times BZ, so I get negative 2 times 5, and then I'm going to subtract off the other two, 1 times 2, and all of this is in the J hat direction, and then I'm going to finish up with the K hat one here. So I get negative 2 times 0, which is 0, and then I'm going to subtract off 1 times 0, which is 0, and that's in the K hat direction. Again, like I expect, no K hat component, because both of these vectors are in the XZ plane, I expect the cross product to only have a Y component. So I'm going to have negative 12 minus 2. Sorry, I already did the math in my head. Negative 10 minus 2. So the negative of negative 12 is a positive 12 in the J hat direction. You can leave on the 0 I hats, especially if you are going to write this in vector form with bras and cats. 0, 12, 0, right? I have a 0K on the end. So like I said, sometimes I revert back to using the determinant of a 2 by 2 matrix or a 3 by 3 matrix in order to figure out cross products. You can write out the formula as I have it written here if you're not familiar with that. It's completely sufficient if and until you learn matrices. So let's do another example. Practicing cross products 2, another example. For A equals, now we have vectors in 3 space. For A equals that and B equals that, find their cross product and the angle between them. Okay, so I know how to find a cross product given the components. I'll just use the second equation, and then it seems like I need to use the first equation in order to figure out what the angle is. So that's my sort of general strategy. So let's just find the cross product. So I'm going to note that my vectors here are negative 4, negative 3, and 1. And I have that. The other one is 2, 0, negative 4. Okay, there's no J component in this one, so I can put that. So I'm going to do the same thing as I did before. I'm going to do a 2 by 2 determinant of the YZs in the I hat direction. I'm going to subtract off the 2 by 2 determinant of the XZs in the J hat direction, and then I'm going to add on the 2 by 2 determinant of the XYs in the K hat direction. Negative 3, 1, 0, negative 4. I'm just filling in the components here. Negative 4, 1, and 2, negative 4. And then the XY components, negative 4 and negative 3, and 2, 0. Okay, so those are a little bit small. I hope you followed what I was doing here. So let's do this one. I'm going to get negative 12 minus 0 in the I hat direction, minus negative 16 minus 2 in the j hat direction, and then I get plus 0 minus a negative 6 in the k hat direction. So when I get done with this, I'm going to have, oh, that should be a positive 12. Thank you for catching that. Positive 12. I have negative 3 times negative 4. I missed the negative in there. So I have a positive 12 in the I hat direction. And then I have a positive, did I do that right? Oh, this is a positive 16. I lost the negative sign again. Positive 16 minus 2 is a positive 14, and then I get a minus 14 in the j hat direction, and then a plus 6 in the k hat direction. So that may be a preview of what issues you may have multiplying these. And like I said, keeping track of signs for me is the most challenging part of doing a cross product, is which terms are negative to begin with because they're a negative component, and am I subtracting them in the actual formula? And so overall, you're going to see that this vector, the cross product, is 12 comma negative 14 comma 6 as a vector. So it has 3 different components pointing off in space somewhere. I'm not going to draw this out, but what I am going to note is now that I have this, if I want to go up and use the first version of this, if I say the magnitude of A crossed into B equals AB sine phi, in order to find the angle, I need to find the magnitude of all these vectors. So again, to find the magnitude of a vector, I'm just going to use Pythagorean theorem, negative 4 squared plus negative 3 squared plus 1 squared, square root it. Everybody okay with that? So I get 16 plus 9 plus 1 under the square radical, and so I get a square root of 26. This one I get 2 squared plus negative 4 squared, square root. So 4 plus 16, that's the square root of 20. And so then this one down here, the magnitude of the cross product is 12 squared plus negative 14 quantity squared plus 6 squared, and I'm going to run that under a square root. And when you do that, I did the math on this already, so you're not watching me do math up here. Keep our time efficient. That's 376 under the radical. So when I plug all of those quantities in order to find the angle, you can see I have this side, square root of 376. I have this side, root 26, root 20, and then that's sine phi. So when I solve this formula, this equation for phi, I get the inverse sine, and just doing a lot of algebra in my head, I'm going to take everything, all of these terms are under radicals, so I'm going to do everything under the radical first and then do the radical. Okay, I just combine all of them under the radical. When you run this through your calculator, you will get the angle between them is 58.2486 degrees. Okay, so I think I can make this look easy. Again, notice what issue I had signs. Watch out for your signs. Make sure you're multiplying the right terms together. That's why I write it out sort of this way, so that I can make sure I'm multiplying the right terms together, because this can be an intimidating formula to use in regard to finding terms. Okay. The last problem I have chosen for us is parallel vectors, right? So we know the dot product is a measure of how perpendicular to or how parallel two vectors are. With a cross product, I know that when two vectors are parallel, the cross product is 0. And when I look at the result, right, if I have 0 in the I hat and 0 in the j hat, and 0 in the k hat, I have to have 0 values in all of the dimensions of that cross product in order for those two vectors to be parallel to one another. So when they're asking this problem here, the vectors A is a 3-space vector and B is a 3-space vector. Notice that they don't have values in vector B. They have Y and Z, and they are asking what are Y and Z that would make these two vectors A and B perpendicular to one another. So what I'm going to do is shoot for solving for Y and Z such that all of these components are 0. Okay, so let's do the cross product. In order to get this to set things equal to 0, I actually have to do the cross product. So I'm going to write these out. Let me write out the 3 by 3 determinant vector here. I, J, K. Okay, then I have 8, 5, negative 6, and 7, Y, Z. So the cross product is the determinant of this matrix. Just to clarify, like if I'm trying to find the first component here, I hat component, I'm going to cross off that row and this column, and I'm left finding the determinant of that matrix, that 2 by 2 matrix. 5, negative 6, Y, Z in the I hat direction. Okay. Let me get rid of this stuff in here so you can see how I do the next one. The next one in here. Let me do red. And I still need to erase this. Get rid of that. Okay, so let's do red. Then if I'm doing the J hat component, I'm just going to go to the J hat in the first row and cross off those two. And then I'm going to do a 2 by 2 matrix of those. So I'll go minus 8, negative 6, 7, Z, and that will be in the J hat direction. I'm going to do the same thing here for the K hat component. Let me get rid of that stuff and choose a different color. Green's always good. That's a good third color. So then I'm going to do, this will be in the K hat direction. So that's how I get this. I go over to the K hat here and I get rid of that row and that column, and then I'll be finding the determinant of that matrix. 5, 7, Y. Okay, so that's how I do those. I did on the previous slide a little bit quicker, and you can see the mechanics of it better there. Okay, so I'm going to do this. I get 5Z plus 6Y in the I hat direction, right? I do a cross multiplication, and I subtract the second term, so minus 6Y minus a negative 6Y becomes a positive. Minus, let's do, multiply this out here. We get 8Z plus 56J, 42. That was a grave error I would have made. Make sure you're multiplying. 8Z minus a negative 42 becomes a plus 42. You're going to do the same thing here. 8Y minus a positive 35 in the K hat direction. So what we want, and what I mentioned before, is we want each of these expressions equal to 0. If these two vectors are parallel to one another, the whole cross product will result in 0, like I said before. So 5Z plus 6Y equals 0. That tells us a relationship between Y and Z, but it doesn't tell us the actual values. This gives us 8Z plus 42 equals 0 and 8Y minus 35 equals 0. So it seems like from this equation I can solve for Z, and from this equation I can solve for Y. So Z will equal negative 42 over 8, and Y equals 35 over 8. I'm just going to leave those as fractions. You could simplify them if you want. They do become decimals, actually. What is this? Negative 5.25, and this is 4.375. And those are the values of Y and Z that would cause these two vectors to be parallel to one another. So you may get a question like that, see a question like that. I really enjoy that question. Just overall, you know, it looks like a complicated question, but just remembering that I want if they're two parallel vectors, the cross product has to have 0 in each direction. So I hope you enjoyed this video about multiplying vectors, and good luck and have fun out there doing math.